This section examines combustion control. Approximately 60% of emissions from an uncontrolled vehicle engine come from the exhaust, a result of combustion of the fuel and the air. To reduce these emissions, some devices or systems control the combustion process itself, while others treat the resulting exhaust gases. Most modern vehicles use a combination. Carburetors meet emission standards by maintaining accurate mixture control over a full range of engine conditions. To achieve this, most carburetors require an air supply at constant temperature. A heated air inlet system uses hot air collected from near the exhaust manifold and mixes it with outside air. One control system uses a temperature-sensitive valve inside the air cleaner. It operates a flap that blends the hot air with cool air, so that the carburetor receives air at about 40 degrees Celsius, regardless of outside air temperature. Maintenance of this temperature assists vaporization of the fuel, particularly when the engine is cold. Vaporization is also assisted by heating the intake manifold, normally by circulating hot liquid coolant through passages in the manifold. If a manifold is too cold, fuel condenses on its inner surfaces, which will create a lean mixture and may cause incomplete combustion. Carbon monoxide and hydrocarbon emissions are highest from a cold engine. Changes in operating conditions can change mixture conditions within the manifold. If a carbureted engine is being driven at moderate speed and the throttle is suddenly closed, any fuel condensed on the manifold walls is drawn into the cylinders. The low pressure in the manifold also acts on the idle circuit in the carburetor to cause a larger amount of fuel to flow from the idle discharge port. All of these factors enrich the mixture entering the engine. There is only a relatively small quantity of mixture in the combustion chamber at this point, so turbulence tends to be poor. This can lead to incomplete combustion and the release of unburned gases into the exhaust. The throttle positioner and dashpot slow down the rate of closure of the throttle plate. This allows more time for air to enter the manifold and for the fuel to vaporize before the throttle is completely closed. A more combustible mixture is thus formed, which leads to complete combustion and a reduction in hydrocarbon and carbon monoxide emissions. Combustion chamber design can affect the combustion process also, and therefore the level of emissions. Designs that increase gas flow rate and promote vaporization distribute the fuel more evenly in the combustion chamber. Quenching of the combustion flame can occur in zones in the combustion chamber where surface temperatures are low. The flame temperature drops so low in these areas that the flame goes out or is quenched. Fuel left unburned in these zones is then exhausted as hydrocarbon and carbon monoxide emissions. If the spark plug is positioned so that the flame front travels evenly through the combustion chamber, combustion is more complete. Gas flow rate and volumetric efficiency can be improved by using 2 intake valves in each cylinder. The effective port opening is increased and the gas flow rate increases. Changing valve timing also alters the combustion process. Reducing valve overlap reduces the scavenging effect. It also reduces hydrocarbon emission. If valve overlap is maintained or even increased, oxides of nitrogen can be reduced by an exhaust gas recirculation or EGR valve connected between the exhaust port or manifold and the intake system. If engine conditions are likely to produce oxides of nitrogen, the EGR valve opens, letting some gases pass from the exhaust into the intake system. During combustion, These exhaust gases absorb heat from the burning air and fuel. This lowers peak combustion temperatures, which reduces the formation of the oxides of nitrogen. The EGR valve usually opens when the engine is at normal operating temperature and likely to be using a lean mixture. When the engine first starts and until it warms up, a temperature-sensitive valve prevents manifold pressure reaching the EGR valve and stops it from operating. Manifold pressure reaches the valve when the engine is warm and when the EGR port at the carburetor is influenced by the position of the throttle. This is generally at light throttle openings, when a lean mixture could cause increased oxides of nitrogen. It does not operate at idle or at wide open throttle. Oxides of nitrogen can also be reduced by retarding ignition timing. This lowers the maximum temperature reached during combustion. The maximum ignition advance setting is then said to be emission limited. However, it also lowers engine output and increases fuel consumption. Spark control systems use ignition timing to optimize engine output and fuel consumption with minimal emissions. They control vacuum levels to the vacuum advance unit on the distributor. In some designs, vacuum signals are delayed with vacuum valves in the signal line. In other designs, the vacuum signals are sustained. The signals can also be applied to dual diaphragm advance units on some distributors. The degree of control needed depends on many other factors, and each application should be considered individually. If the exhaust gas is hot enough, combustion of remaining hydrocarbons and carbon monoxide can be completed by adding extra air to them at the exhaust port or manifold. This afterburning produces water and carbon dioxide, which are then exhausted to the atmosphere. The pulse air method uses the pulsations of the exhaust gas to open and close a reed valve. It admits air into the exhaust manifold in short bursts. Air drawn from the air filter enters the exhaust manifold. This method suits engines with 4 cylinders or less because their exhaust pulsations are further apart. Larger capacity engines may use an air pump to supply a larger volume of air. The pump is normally driven by a V-belt from the engine crankshaft and forces air into the exhaust ports. Some of the engine's output is used in driving the pump. Electronic fuel injection and engine management systems deal with emissions more effectively than carbureted engines by more closely controlling the air-fuel ratio entering each cylinder and by ensuring the ignition timing matches operating conditions. Sensors around the engine send the ECU information about airflow, coolant temperature, throttle position and engine speed. The ECU uses this to set fuel and ignition settings from its programmed memory. Most systems also use a sensor in the exhaust manifold to gauge the amount of oxygen in the exhaust gases leaving the engine. This indicates how well combustion is being completed, which in turn indicates the air-fuel mixture entering the engine. A voltage signal is then relayed back to the control unit to indicate whether the mixture is rich or lean. More oxygen indicates a lean mixture. Less indicates a rich mixture. The control unit then adjusts the amount of fuel being injected into the engine to keep the air-fuel ratio very close to the chemically correct composition for complete combustion. By mass, this is 14.7 parts of air to 1 of fuel, known as the stoichiometric ratio. Maintaining the stoichiometric ratio within close limits is necessary for the catalytic converter to operate efficiently. It fits into the exhaust system like a muffler near the exhaust manifold. It receives all of the exhaust gases from the engine and chemically treats the remaining pollutants in the gases, converting them to less harmful substances. This is done by a catalyst in the converter. A catalyst causes a chemical reaction, but after the reaction ends, remains unchanged itself. The catalytic converter has a ceramic core housed in a stainless steel shell. The core contains many small passages through which the exhaust gases pass. A thin coating of aluminium oxide called alumina wash coat covers these inside passages. It has a rough surface, and it's there to provide a large surface area in the passages. The catalyst is finely dispersed over the surface of the alumina wash coat. The large surface area ensures that virtually all of the exhaust gases come into contact with the catalyst as they pass through the passages in the core. Leaded fuel cannot be used in vehicles with a catalytic converter. The lead contaminates the catalyst and stops the reactions from occurring. The use of unleaded fuel has a further benefit of reducing the amount of lead emitted into the atmosphere. Diesel engines are usually low in carbon monoxide and hydrocarbon emissions, though some do emit high levels of the oxides of nitrogen. The main problem with diesel engines is the emission of particulates, minute particles of carbon, visible as black smoke. Most diesel engines of heavier vehicles use electronically controlled injectors. This has reduced considerably the emission of particulates and oxides of nitrogen.